Thank you. Yeah, hello. My name is Alexander. I work at Microsoft as a principal engineer since 2 years and a few months. I'm Postgres contributor. Like you also may know me as maintainer of Patroni, like a solution for PostgreSQL high availability, or like some people call me the Patroni guy. You can write me by this email in case if you have like questions regarding this presentation, Postgres HA, replication, or just like whatever other question I can try to answer. At Microsoft, unfortunately, I'm not responsible for HA part, but like I'm deeply involved right now into flexible server, which is mainly Postgres, the same Postgres as you use when you install it from normal packages or for, like compile it on your own. And this talk is about some myths and truths that I managed to collect while answering question about like synchronous replication and how Patroni works and like how just Postgres replication works, because sometimes people have unexpected estimations about like its work and so on. And to start this talk, I want to introduce a little bit of dictionary or like explain about write-ahead lock in the beginning. So what is it about? Like write-ahead lock, or like in Postgres, you may see it as wall. It's a standard method to ensure data integrity, and it is used to naturally provide recovery, archives, replication, and so on. Like you can read a bit more in details in Postgres documentation. Here is a link. And if you run a Postgres cluster and you look into pg wall directory, this is the place where Postgres stores write-ahead log files, you will see something like this. There will be files, a list of files. Every file name has 24 characters. Like the first 8 are used to define a timeline, which is right now not so important, and the rest, like again, split into 2 parts and basically defines at which specific LSN this log belongs to. And if you just initialize your database to, like by default, every write-ahead log will be 16 megabytes in size, like on this picture. As I said, based on write-ahead logs, there are many things could be built. And once write-ahead log was introduced, it became possible to use it for continuous archiving and, of course, point-in-time recovery. Or like you can build log shipping replication. How does it work? When Postgres finished writing a single log file, for example, this one, which ends at 7, it switches to the next one, which ends at 8, but at the same time, it will call archive command, which, and specify that so I want you to copy this file to some external storage, to some safe place, and in case if standby node needs this file, it will call restore command, again specifying the file name which I need to restore. And restore command should extract this file from a safe place and write it to a proper location, which Postgres is asking for. And on top of write-ahead log, there is also streaming replication mechanism, which is built in Postgres since version 9.0. Version 9.0 implemented only physical replication, and in fact this talk is focused on physical replication, but starting from 9.4 version, it's also possible to use write-ahead log to logically replicate data from like Postgres to some, maybe Postgres, maybe some other database, or like your application could extract logical changes from write-ahead log. So how does it work if we look at Postgres like as processes in the, and some devices on the server? Like we get a primary server on which we have Postgres and a bunch of auxiliary processes, including a process which is called wall sender. And on the standby node, we also have a bunch of auxiliary processes, and one of them is wall receiver, and another one is a startup process. When standby is configured to replicate data from the primary, it first starts a wall receiver process, which will connect to the primary, and primary in response start a wall sender process. Wall sender process is what is effectively doing, it's just reading from file system, from pgwall directory, and sends this data over TCP to wall receiver. Wall receiver, what it does, it sends writes this data to files on the file system, again to pgwall directory, and it also notifies wall sender about the state, its own state. Literally, it says, I wrote up to a very specific point to pgwall, and primary knows like how standby is progressing. There is also startup process on the standby, which reads data from pgwall and applies it to the database. Basically, only after startup process applied data on the database, you can see those changes on the standby node, like when you query it. Without it, it wouldn't work. And streaming replication, like by default, is asynchronous. Like, what does it mean? When primary writes something to pgwall and wall sender sends this data, it doesn't wait from a standby to confirm that I received and maybe applied those changes. So it just writes it and forgets, like without waiting for any feedback. In case of synchronous replications, things work slightly different. When primary receives a commit, it will not notify a client until this commit is received by sufficient number of standby nodes, and maybe, like depending on the configuration, it will wait until standby node not only wrote this data to disk, but also flushed, like using fsync mechanism, or maybe even applied, so it became visible if you run some queries. And there are two configuration parameters in Postgres that control behavior. One of them is a synchronous commit, and in order to enable synchronous standby, you should be using one of three possible values. It's either remote write, on, or remote apply. And in synchronous standby names, you need to list standby nodes which you want to get feedback from before transaction is considered committed. Let's take a look closer at those configuration parameters. Like synchronous commit, in fact, it's an enum which can accept 5 possible values, and depending on those values, you may get different behavior. Like if you set synchronous commit to off, primary will not write any, like will report transaction as successfully committed even without writing it properly to disk. Like in case if you set it to local, it will write it to disk, flush, and only after that client will be notified that your data is committed. And in case if Postgres crashes, you will be able to successfully apply write-ahead lock, and you will still see this transaction as successfully committed. And synchronous commit, which is important for this presentation, starts like when value of synchronous commit is remote write, like or higher. By default, synchronous commit is set to on, which means that it is durable on primary node, and at the same time, it is sent to a standby node, and also durably written to a storage on a standby node. So it means if Postgres, for example, crashes, it will be able to, like on standby node, it will be able to restore everything. Or like if the entire server crashes on the standby node and like you start it up, there is a guarantee that you will be able to restore up to this transaction, which was reported as successful to the primary. And the highest value of synchronous commit is remote apply. It means that if you run a query like that wants to access data written by exactly this transaction, you will get a consistent response from a standby node. And the second parameter is a synchronous standby name, which allows us to define type of synchronous replication. And at this moment, there are two types of synchronous replication. It's a priority synchronous replication, which exists since Postgres 9.1. In fact, in 9.1, this parameter was still called synchronous standby name, and it was possible to specify only a single node. Now it's a synchronous standby names, and you can specify some list of nodes or maybe asterisks, and you say, I want transaction to be successfully reported to the client only when some number of nodes from this list confirm that they received and maybe flushed or applied this data. Like in this example, if node 1 successfully received transaction and confirmed it back to the primary, it will be considered as successfully committed. In case if node 1 fails, primary will wait for confirmation from node 2. Kind of works, but there are problems because it does it sequentially. To improve this situation, there is a second type of synchronous replication named quorum replication or quorum commit. The synchronous standby names in this case look slightly different. Instead of first we use syntax any, then number from how many nodes we need to get confirmation. And on this slide, it will be reporting transaction as successfully committed when like node 1 or node 2 sent a confirmation to the primary. When primary receives this confirmation. Basically, in case if one of those two nodes fails, primary will not experience any issues. Because like it may take time to detect in case of priority replication that node 1 is not responding. So it's clearly more beneficial to use quorum commit. And now we come in to most interesting part of this presentation. People believe that transaction is committed only synchronous standbys confirmed that they received and maybe applied this transaction. So do you think it's a correct statement or not? Please vote, like if you think that's a correct statement. Okay, not so many hands. So what happens in fact? Transaction is like always like committed and written to write-ahead lock on the primary first. So it's literally durably written to disk, and without doing this, you cannot replicate commit record to the standby node. This is how replication works right now. But what's important, primary holds some locks, and this transaction is not visible to other connections on the primary until those locks are released. And those locks are released only when sufficient number of standby nodes confirmed that that they received this commit record. However, there is a problem. Like on the primary, it's possible to cancel query or like terminate connection, or maybe application somehow broke, and it also results in TCP connection being broken. Basically, backend on the primary that is responsible for handling this connection will exit, and logs are also released. It means that, or for instance, the whole Postgres is restarted, and in this case, all connections will be recreated, and again, transaction becomes visible to other connections in this situation. So just to explain it a bit more nicely, I created this diagram. So like what happens when application issuing commit to the primary? We get some logs holding this transaction from being visible to other connections on the primary. Primary writes commit record to PGWall. Then wall sender on the primary reads this record from PGWall. And at this time, logs are still being in place. So other connections on the primary cannot see those changes. Wall sender sends data over the network to the standby, to wall receiver, which writes it to PGWall. Then startup process reads those records, applies them. Wall receiver will get notified that commit record was applied, send back some feedback to wall sender, and only after that, wall sender will notify and release logs on the primary, and transaction will be successfully reported back to the application. So it's a big loop which increases latency. However, like let's consider like very simple situation. Like we set synchronous standby names to some value which is name of unknown node, which does not exist on the system. Like you can do it just on a single node Postgres. And we reload configuration. Like after reload, we can check that indeed synchronous standby names was changed to unknown. We check synchronous commit setting, like it's on. It means transaction should not be successfully reported to the client until synchronous standby with name unknown reported it back to us. And like when we try to create a table, this query will stuck, more or less. But you can cancel it by pressing Ctrl+C, like it's a PC call, by the way. And right now, Postgres giving some hints that cancellation for synchronous replication, so wait for synchronous replication was canceled because of user request. But transaction is already committed locally. And if we run a select after canceling query, we see that table exists. It has expected number of rows. But we know for sure that this data wasn't replicated. So coming to the second myth. Some people think that synchronous replication guarantees zero-point recovery objective. Basically, when we use synchronous replication, there will be no data loss if we have to do a failover. So do you think it's correct? Well, it depends. Like it depends on some factors. Application may change synchronous commit setting, like per connection. It's a good thing, it's maybe not a bad thing per se, but applications can do it. They may say, all right, so this transaction for me is not important. I don't want to wait until it is replicated and confirmed by synchronous standby. Therefore, I'm going to disable. But at the same time, you don't know. Maybe there are other applications that are relying on those on this data, and since it will be immediately visible on the primary node, other application may do some decisions based on that, and at the end it may end up in data loss. Also, like as I said, query could be cancelled by application itself, or TCP connection could be broken, which immediately makes transaction visible to other connection, or Postgres could be restarted. So why is it a huge problem? Like if let's imagine that our application is behaving correctly. It's not changing synchronous commit setting, like to local or even worse to off. And it's not canceling, like actively canceling its query. It's not using statement timeout or stuff like that. But something happened with the network. Like our world is not ideal. Like some network hardware could also fail, and our TCP connection got broken. And this transaction becomes immediately visible to other connections, and they may do some further changes based on it, even without realizing it, because you may do, let's say, insert on conflict update. And in case if primary fails, then this data will be lost, because there are chances that it wasn't replicated to a standby node. There is a discussion on hackers' mailing list about disabling cancellation of such waits for synchronous replication. And it's known problem, and as far as I know, most of, if not all cloud vendors have custom-made patches, and Postgres running with such patches that allows canceling such waits for synchronous replication to avoid the problem of data loss. So let's imagine that our application did not cancel query actively, but just TCP connection got interrupted. And application should be built in a way that before retrying it, supposed to check state of the transaction and like before continue to work. There are two ways of doing this. Like one could use a two-phase commit, which is kind of very heavy and requires special coding or in the application. Or for instance, you can use a built-in function which allows to check state of transaction, like whether it was committed, aborted, or it is still in progress. What's important to know about this function, it works only for some recent transaction. If like transaction was a long time ago, this function will return null. So how does it work? Like we start a transaction, we do some data changes in transaction, and before committing, we select current transaction ID. So in this example, we created a table again, and this is a transaction ID, like which was before commit was hit. And it's number 764. In a separate connection, we actually can check in pgstat activity like what is going on with this transaction, and we can filter it by backend XID. And what's interesting, it will be saying you that it is waiting for synchronous replication. And this is still configuration from one of the previous slides with unknown synchronous standby. In this case, I just killed my PSQL process and waited until TCP, like Postgres will realize that TCP connection is broken. When I reconnect with PSQL, I'm checking status of this specific transaction, and it says it was committed, but client didn't receive any notification while was waiting for commit. So this is the way how to check that transaction was committed. Yeah, so the next myth. People think that reading from synchronous standby node is like reading from the primary. So they say, like, all right, so I'm gonna use synchronous standby nodes for reading and primary only for writing. So do you think it's a correct assumption? All right, I'm not gonna wait until some hands show up. In fact, it's not entirely correct. The problem is that transaction on any standby is immediately visible once it was applied there. Let's say you have a primary and primary is waiting for two synchronous standby nodes to confirm commit. One of standbys already received and applied this transaction, and if you query this standby, you will see this data. But if you query the primary, it will still not be visible. So it's a very funny side effect. Not many people aware of it. Like, and if you build in your application, you should never decide to do writes on the primary based on reads on a standby, even if you are reading from synchronous standby. So what is even more funny is that asynchronous standby, in fact, could be ahead of synchronous nodes. They could be applying commit records faster than synchronous node. And let's say primary is still waiting for synchronous standby names, for synchronous nodes to confirm, but primary failed. And synchronous standby could be behind the asynchronous node, like it's possible. In fact, logical replication exhibiting very similar behavior. It could go ahead of synchronous nodes. So, like when your application is relying on logical decoding, like receiving changes and stuff like that, it could see some features that never happened because primary failed and synchronous standby was promoted. And right now in Postgres 17, there is a nice solution for it. Like you can create a logical replication slot and say, I want to use failovers, and you need to tweak some other Postgres configuration parameters for it to work, which says before logical events will be sent to a client, we need to wait until some synchronous standby names received and confirmed those events. Or, like in case if you are not on Postgres 17, but on something older, you can use PG failover slots extension from Enterprise DB. It's open source extension, and I would recommend like using it. Like I either run fresh Postgres 17, or in case if you use something older, like please please use this extension. And another problem, like when you want to read from synchronous replicas, like with quorum-based replication, you have no clue which nodes are synchronous, because, like, let's say you have 4 nodes listed in synchronous standby names, and you are waiting for 2 of them to confirm, and like you just don't know like which exactly were synchronous at this moment. Like you may end up reading from the node that did not yet receive this commit. So, like when it's safe to like read from standby after writing to a primary, one case is very simple. When you have either first or any, and the number in synchronous standby names matches with the number of nodes that are listed. It more or less guarantees that transaction like made to like all of them. Or otherwise you need to wait until standby fully caught up, like with some specific transaction. To do this, like there are 2 approaches. Either you can memorize PG current wall insert LSN while committing transaction on the primary, and then waiting until standby replayed up to this LSN. Or you can also use TXID status, or like was on this slide. Basically, this function also works on standby nodes. And it would be nice to have in Postgres something built in. Instead of just doing in a loop such function calls, to have function, please wait until specific LSN is like replayed, or until transaction is applied. So another myth, like number 4, we just need to promote a synchronous replica or synchronous standby to avoid data loss. Let's assume like our application is behaving correctly, there are no surprises, like we built everything with our own hands and it's reliable. So do you think it's true? Like, can we just set synchronous standby names to some value and promote node which was listed in synchronous standby names? So, like, what may happen, in fact? Let's assume situation. We have a primary, node 1, and node 2, which is right now asynchronous standby. We change synchronous standby names parameter and set it to node 2. We call pgreloadconf to reload Postgres configuration. And like suddenly, right after pgreloadconf, our node 1 crashed, like completely. Do you think latest transactions made to node 2? Like, was it really fully synchronous node that primary like was already waiting until this node starts confirming transaction before reporting them back to the client, to the application as successful? So, in fact, we cannot know, and we need to prove that like this node became synchronous. How, in my opinion, it should work, and I think some other people who built high availability solution confirm this opinion. Like after changing synchronous standby names, like and changing Postgres configuration, we need to wait until this parameter becomes visible. Like when you do show synchronous standby names, it will show the value that you set after doing reload conf. And you need to memorize LSN returned by pgcurrent wall insert LSN at this moment. And after that, you need to wait until standby either received, flushed, or applied write-ahead lock up to this LSN reported on previous step. Basically, only at this moment we can know for sure that it became fully synchronous and primary was already waiting for this specific synchronous standby name. And only from this moment it is safe to promote synchronous standby. And you can say with 100% certainty that you didn't lose any data which will be like visible to clients. So also people really making a big mistake thinking that if we use synchronous replication, we don't need to have pgrewind. Unfortunately, it's not entirely true, because write-ahead lock is written independently from standby nodes. And in fact, like write-ahead lock contains not only commit records, it contains all kinds of records, including, let's say, after vacuum and all other changes. Like, let's say you do a huge bulk load, like copy, and there is a transaction in progress, but some commit record could be inserted like in between, and it could perfectly happen that standby didn't receive some parts of wall. Those transactions were never reported successfully back to the application or to the client. And when we promote standby, there will be no data loss from perspective of the client. However, like standby will be behind the primary that failed, or it could be like a little bit behind, like of some other standby, even synchronous standby. Like of course, like in order to reconnect one synchronous standby as like to the new primary, like we can do proper checks and promote only the node which was most ahead. But like, to join the old primary, you still need to run pgrewind. There is no way around it, because it could have been a little bit ahead. Like even a few bytes are important. So yet another myth, which is probably not so myth, like synchronous replication is slow. Like people constantly saying it, and to actually prove it or like disprove, I decided to do some benchmarks. Like I put double quote on benchmarking word on the slide because benchmark was done on my laptop for simplicity. I just used Docker Compose with 3 containers and Postgres running in containers. And in order to emulate latency, I was using IP root utility. So Postgres configuration was default. I didn't really wanted to like have fully blown benchmark, so I increased only max connections because I did a series of tests with PGBench with scale factor 100, and like every test was running for 60 seconds. And settings of synchronous commit and synchronous standby names were the following, like either like priority synchronous replication or quorum synchronous replication to a single node, like out of 2. Like asterisks here like is not dangerous because we know, like in this case I knew for sure that there are only 2 standbys. And I was doing it with like different connections from PGBench to Postgres with different number of connections. Started from 10, then increased it to 50, 100, and so on. So, and here are the results. Like if we if synchronous replication is not enabled, initially the transaction rate was around about 2000, and latency was 5 milliseconds. Like when I enabled synchronous replication, like the priority one, latency became 14 milliseconds because like it more or less double latency, like double disk latency, like because it's on the same machine, and plus like 1-2 milliseconds on top. And with quorum replication, latency was a little bit smaller. Like with growing number of connections, of course, TPS for synchronous replication is increasing, but probably on this laptop it's not so nice, like it's not looking so nice. It should be a real setup, but in fact, I hope it's gonna be approaching the asynchronous replication. And like asynchronous replication, as you can see, it maxed out after a certain number of connections. But it's my laptop, it's not powerful enough. When I increased latency from 1 millisecond to 5 milliseconds, like what becomes interesting, the latency of priority and quorum sync increased. Like it was 12 and 14 milliseconds, like with 10 connections, and then it became 18 and 19 milliseconds. Basically, it increased around about this round trip between nodes. And but transaction per second, sorry, yeah, it became a little bit smaller. When we increase latency even further, like round trip between nodes, then latency on the primary, like of transactions on the primary is growing also further up. It's not interesting to look at like 250 because my laptop simply can't handle it. But I think the picture, like and how it evolves, like tells about itself. And what is the most interesting part, like when latency, when round trip between nodes is 100 milliseconds. In this case, I was able to reach with synchronous replication only like 700 transactions per second. Basically, what is the conclusion from this benchmark? Like, in fact, like the speed of replication remains the same because like it's just TCP connection. Like, and if connection can like handle, let's say, I don't know, like 10 megabytes per second, it like will remain the same. But like if we count transactions per second that we see on the master, on the primary, it will be less when round trip between nodes is increasing. So It means please don't run synchronous node which is between different continents where latency is very high. Like you will just ruin your performance of your application. And in most cases, additional latency for queries coming from the fact that they need to wait until synchronous standby name received, like flashed or applied transaction and reported back. However, you can still scale TPS by increasing connections from the application. Like it's certainly growing. Like of course it will max out at some point, but it scales. However, like final transaction per second will still be lower because Postgres will spend additional time like handling lightweight logs and so on while waiting for reply from synchronous standby nodes. Yet another thing where Postgres is not so flexible, I would say quorum commit feature is not like should be also improved. Let's consider a situation where we have like 3 data centers, like 3 availability zones, and we run our nodes across different availability zones. And we want to distribute our data more or less evenly. We want to have something like, so that synchronous nodes will be like in every data center. Like, of course, like primary is in AZ1, but we want to have synchronous node in AZ1, AZ2, and AZ3. But right now, the only way to do it, just list nodes in synchronous standby names which supposed to be synchronous. But like with such configuration, what may happen that synchronous nodes will be just in 2 availability zones, like AZ1 or maybe like AZ2 or maybe AZ3. Like it's totally possible, and there is no way to influence it, unfortunately. So yeah, I have a few bonus slides. Like so, what to do in case if we need to fail over to synchronous standby nodes? Like in case if it's our synchronous standby names is like in a format n and then the same number of nodes, like n nodes, we can basically pick any node and promote it, and there will be no visible data loss in case if application isn't doing anything terrible, like disabling synchronous commit. However, it's better to choose the most up-to-date nodes so that we don't have to do PG rewind on the rest. Like if we promote not the most up-to-date, the rest must be rewound. In case if we have something like this, like when, let's say we are waiting for 1 node to confirm out of 10 nodes, then we need to query all of them and get responses. And the formula is like m minus n plus 1. So how does it look on picture? Let's say we have primary and 4 nodes, like 2 of them synchronous and 2 of them are asynchronous. And in synchronous standby names, we have something like any 2 out of those 4. Basically, to find which node, like to find with 100% certainty one of the node which was synchronous when primary failed, we need to see at least 3 nodes. So this is just pure math. Like if we see, if we can access less than 3 nodes, it could be that we will find only asynchronous. So you understand the idea, I hope. Yeah, so basically I'm done. Like if you have questions, now it's time. I hope you didn't get bored, and I hope you learned something, and some of myths were busted.
Hi, I would like to ask what was the names used in standby? Is it the name of the replication slot or what?
So, like replication slots are a bit orthogonal to synchronous replications. Like in order to run replication, you don't need to have replication slots. That's important.
Okay, so what are the names used in synchronous standby names?
Those are names of nodes, and they basically need to provide in connection string as application name equals like some random name, and primary sees them as under those names. I don't know, so I don't have slide for it. So like when standby is configured, you need to provide primary con info, like so basically connection string where you want to replicate from. It contains host name, port, of course username, like maybe some credentials, maybe certificates, but optionally you can specify application name. And this application name should be matching name of your synchronous standby. And primary, when processing synchronous standby names configuration parameter, it basically picks among nodes with by application name they use.
Thanks.
Does it answer? I hope it does.
Ještě někdo? Queries? No query? So thank you very much.
Yeah, thank you.